There was a question earlier of like, what does the dot product really tell us? To really get insight out of what the dot product means, it's useful to look at its alternative or equivalent definition. And now this is something you saw in Math 18, and the kind of thing you would do there is prove that these two things are equivalent. Well, I mean, I don't know. I don't teach Math 18, so I don't know if that's what they do there, but these two things are equal. These two definitions of the dot product are equal. Okay, so one definition is this like sum of element-wise products, but the other is length of the first vector times length of the second vector times the cosine of the angle between them. Sound familiar? Okay. And so why do we need two definitions of the same thing? Well, the key idea is that it helps us find the angle between the two vectors. Right? Because I have a way of writing the dot product in a way that doesn't involve angles, in a way that I can do pretty straightforwardly, and another way that does involve angles. And so what I can do is set this equal to this and solve for the angle between the vectors. Why is this relevant? Well, we'll start to see that as the lecture progresses, and as you'll explore this in the new homework that's dropping tomorrow as well. Okay, but let's work through this concrete example. Back to our friendly u and v. U is 2, 4, and v is 5, 3. We can find their dot product in two ways. One, really go and try hard with the color here. One way is by doing 2 times 5 plus 4 times 3, which is 22, as I've already seen. Right? The other way is by doing the length of u times the length of v cosine of the angle between them. Right? Sound okay? Can we find the length of u and the length of v? Yeah, it's not that pretty looking, but we can do it. What's the length of u? Well, it's u dot u plus, this number times this number plus this times this, the square root of all of that. So it's 2 squared plus 4 squareds, square root. So it looks something like this. What's the length of v? Square root of 5 squared plus 3 squared. All of this times the cosine of the angle between them. So what does this end up being? Ends up being square root of 20 times the square root of 34 cosine theta. And again, you're asking, why do I care that this is the dot product? Well, it's not that I'm going to do anything with this in particular, but it's that I also know this is equal to this. And by equating the two, it'll let me find the angle between the two vectors. Okay, which is a measure of how similar they are, or how closely they point in the same direction. Right? If the cosine of the angle between them is 1, well, that means the angle between them is 0, because they're pointing in the same direction. So, let's equate the two. Those must be equal. And so, bringing this up here, we have square root of 20 times the square root of 34 times the cosine of theta is equal to 22, which means the cosine of theta is 22 over the square root of 20 times the square root of 34. Just some, good life advice. How can I simplify the square root of 20 a little further? Yeah, it's 2 times the square root of 5. Where does that come from? Well, 20 is 4 times 5, so the square root of 20 is the square root of 4 times 5. But the square root of 4 times 5, when you pull out the 4, it's unsquare rooted, so it looks like 2 square root 5. So this is really 22 over 2 root 5 root 34. But that cancels, so we get an 11 on top. Okay? So what does this all mean? The angle between these two vectors is the cosine inverse of 11 over root 170. That's the takeaway. Do we agree? The specific number it ends up being, it doesn't really matter to me. I just want to know that I can write the angle as cosine inverse of something, or tan inverse of something. Sound okay? All right. Let's see. Does it sound okay? Take a few minutes, work on it with the people near you. It's the exact same problem, just with slightly different vectors. And I will note, because I mentioned this in the first lecture section as well, question 2a on the new homework is literally this exact question. The numbers are different, but it's the same question. So to the allegations that lecture and homework are not related, there's my answer. This happened in the first class too, that there was like no talking when working on this question, and my theory was that people were so traumatized by Math 18 that they just want to work and not talk when it comes to this. I see a lot of calculators. I don't need to know the actual degree. Like, again, it just needs to be cosine inverse of something. Question, for how many of you has it been over a year since you took Math 18? Okay, good. I should have also noted this was not a multiple choice question, so you didn't have to answer it at the site. But let's work through it. Same principle as the last slide. U is the vector 4, 1, and V is the vector -2, -4. The key idea here is to equate the two versions of the dot product. Right? Same thing we did on the last slide, which is, say, U dot V, just to expose you to it again, I'm going to write it as U transpose V. That's 4 and 1, -2 and -4. Again, just as a reminder, the way to imagine this is I'm taking this and I'm like rotating it and falling into the next vector, right? And this is going to look like 4 times -2 plus 1 times -4. And last I checked, that's -12. Okay? That's the first part. The second way of computing the dot product is the length of U times the length of V, cosine of the angle between them. Okay, what's the length of U? Well, it's square root of 4 squared plus 1 squared. What's the length of V? Square root of -2 squared plus -4 squared. Cosine of theta. So to me this looks like square root of -17, square root of 20, cos theta. The key idea here is that all of that is equal to negative 12. So here's a loaded question. How do I know, just pretend I couldn't see this picture. How do I know the angle between the two vectors is greater than 90 degrees? Pretend, again, this picture's not there. I'm covering it up. How do you know the angle between the two vectors is greater than 90 degrees? Chirag. No, but you're not allowed to look at the picture to answer this. Just by what's over here, how do you know the angle is greater than 90 degrees? Yeah.
If it is 90 degrees, wouldn't it be like, I don't even know if it's the right way, the reciprocal of each other? So this is like...
I think you're looking too carefully at the numbers. There's a simple fact about them that tells you the angle is greater than 90 degrees. Yeah.
Is it that it's negative?
Yeah. It's that the dot product is negative. Why does that tell me that? Well, let me show you. What I'm going to do is equate these two things. And I'm going to say the square root of negative 17 times the square root of 17, times 20, cos theta is negative 12. Which means cos of theta is negative 12 over the square root of 17 times the square root of 20. Rewriting this as 2 root 5 again lets me pull out a factor of 2 from both the numerator and denominator. And I write this like that. Okay? And if I want, I can simplify this even one more step. Call this negative 6 over root 85. Okay, which tells me the theta is the cosine inverse of negative 6 over root 85. Whatever that ends up being. Do we agree? Okay. Now, how did I know that the angle is greater than 90 degrees? Well, my claim is that because it's negative, I know that. Okay, but why does it being negative tell me that? Well, we're going to bring back our good old friend. Get ready for this one. The unit circle. Okay? And remember, for any angle theta here, the x-coordinate on the circle is the cos of theta. And maybe I'll put this in blue. Try to make this drawing good for the future. The x-coordinate is theta, or cos theta, and the y-coordinate is sine theta. Right? What is the significance of all of this? Well, if my angle is over here, that is between 0 and 90, or 270 and 360, which is over here, well then the cos is positive, because the x is positive. And if the angle is between 90 and 180, well then the cos is negative, because the x value is to the left of x equals 0. Okay, so if I have an angle greater than 90 degrees and less than 270, well then its cosine will be negative. And in this context, I don't really have to worry about the greater than 270 degrees case, because I could just put the angle on the other side and it would be 360 minus that. Right? It's just like I wouldn't put this theta over here. It makes more sense to put it here. Even though the cosine of this angle is the same as the cosine of that angle. Right? By this picture. Cosine of theta is equal to the cosine of 360 minus theta. Sound okay? All right. So anyways, all of that was to say I could tell the angle between the two vectors was going to be greater than 90 degrees by virtue of its cosine being negative. Okay? Now, the cosine of the angle being positive or negative is not as important as knowing that the cosine of the angle is 0. Okay? The cosine is 0 when we're looking at a right angle or a 90-degree angle. And that happens here. Right? If I'm at this position up here, theta equals 90, my x position right now is 0, which means the cosine of 90 is 0. What's the sine of 90? 1, right? Because the height here is 1. So here's some facts. The cosine of 90 degrees is 0. But also, the dot product can be written as length of first vector times length of second vector times cosine of angle. But if the angle between the two vectors is 90 degrees, well then the cosine will be 0, and so the dot product will be 0. Okay, so if there's a right angle, the dot product is 0. Do we agree? Okay. Now, if we have vectors in 2 dimensions, we say that a right angle means that they're perpendicular. So we might say something like there's a right angle, meaning that they're perpendicular. But in higher dimensions, we say that 2 vectors with the right angle are orthogonal. Okay? But here's the key idea. 2 vectors are orthogonal if and only if, that's what this bidirectional symbol means, their dot product is 0. And this being a bidirectional symbol means these are equivalent conditions. They're orthogonal when their dot product is 0. And their dot product is 0 when they're orthogonal. I can take one statement and it implies the other one. Do we agree? Okay. I mean, that's under the assumption that the 2 vectors are not just the 0 vector. Okay? So some things here. Because the 0 vector's dot product with anything, well, is 0. Okay? And this if and only if means it's a bidirectional statement. So their dot product is 0, they're orthogonal. If they're orthogonal, their dot product is 0. Okay? I might even remove this condition because maybe, not that it's super important, but I feel like by convention they'll define the 0 vector to be orthogonal to every other vector. So you don't need that condition. Okay? But big picture idea, if there's a right angle between the 2 vectors, their dot product is 0. Do we agree? Okay, so to test this out, here's an exercise. Find any vector in 3 dimensions that's orthogonal to this one. There's infinitely many possibilities. Find one of them. Infinitely many. Okay, any ideas? Yeah.
Would 2, 12, 8 work?
Yes. We could do 2, 12, 8. How do I know it works? Well, the dot product would be 2 times 2 plus 12 times 5 plus 8 times negative 8. That's 4 plus 60 minus 64. Good, that's 0. Okay? Now, here's what I did. And I guess the weird consequence of this being the second lecture section is I know what I did in the first lecture. But when I did this in the first lecture section, I intentionally didn't come with a pre-prepared answer myself. And so while people worked on it, I came up with my own answer. And I tried to do this the easiest way possible, which is by setting one of the two equal to 0, or one of the three equal to 0. Because I just said, you have to find a vector where they're not all 0, but some of them still can be. And so I just said, okay, for simplicity, just make the first one 0. Well, then I could just do 8 and 5. And the 5 times 8 would cancel out the minus 8 times 5. Okay? So it's just another option. Okay? A student in the first section mentioned that they did it by finding solutions to 2u1 plus 5u2 minus 8u3 equals 0. And that's really all this boils down to.